We'll consider some examples of application of the subgroup tests. In the first example, G is an abelian group and H is this subset of G, all elements X in G such that X squared is equal to E. Prove that H is a subgroup of G. Abelian group means a group with a commutative law for multiplication, for the operation. First, H is not empty subset of G because we know that E squared is equal to E. E is the unity of the group, which means that E satisfies the requirement of being an element of H. So this shows that H is not empty. Next, we select two elements A and B in H, and we want to prove that A, B to the negative 1 is also in H. To that end, we raise A, B to the negative 1 to the second power. If the result is E, then A, B to the negative 1 will be in H. This is A, B to the negative 1 A, B to the negative 1. But because the group is abelian, any two elements commute, so we can swap these two, and we get A squared B to the negative 1 squared, but B to the negative 1 squared is, first A squared is E, because A is in H. It meets this requirement. So A squared is E, and B to the negative 1 is B squared to the negative 1. The result is E to the negative 1, which is of course E. This proves that AB to the negative 1 is in H, and the one-step subgroup test guarantees that H is a subgroup. In the next example, G is any group and A is an element in G. So G can be non-abelian group. No restrictions here. Let this way denote, we denote this way the set A to the n, where n can be any integer. So the set of all integer powers of A. Prove that this subset is a subgroup of G. We'll use the two-step subgroup test. First, when n is 1, we obtain A. So A belongs to this set, which means that this set is not empty. Now select two elements A and B in the subset, and prove that their product is also in the subset. I'll take rather A to the n and A to the n, where n and m are integers, because the elements of this subset look like that. They are integer powers. Prove that A to the n, A to the n is also there. Why is this so? This product is equal to A to the power n minus n plus m, and n plus m is integer. That's why, because n and m are integers, the sum is integer. That's why this power belongs to the subset. And the second step, select any element in this subset. So A to the n is any element in the subset, n is an integer. Prove that A to the n, the inverse of this element, is also there. Why is this so? A to the n, the inverse of this, is equal to A to the negative 1 to the n, and I'll rather write it this way. This is A to the power negative n. Since negative n is an integer, we have an integer power of A, which means that this element belongs to the subset defined in the problem. This shows that the requirements of the two-step subgroup test hold. The subset is closed under multiplication and under taking inverses. It is not empty. That's why it is a subgroup.